Hello, everyone. We're Team ME31, and we are the Reduced Gravity Simulator for Field Environments, the mobile frame system team. So, our team is consisting of several multidisciplinary majors, and we are sponsored by NASA to create a mobile frame system that offloads weight. So, let's meet the mechanical engineering team.
Hello everyone, my name is Tayyaba.
I'm Matt.
I'm Luna.
And I'm Daniel Yang. So to give some context, in that image to the right is of Argos. So NASA has a device called the Active Response Gravity Offload System in the Johnson Space Center, which essentially offloads weight on the astronaut so they feel like they're on a different planet. And this is important because astronauts need to practice how to walk, kneel, or jump while on the moon or in space. And you just can't get that without having prior experience. So the biggest drawback for Argos is that it's stationary. It's stuck inside the building at the Johnson Space Center. So our task is to design and build a mobile reduced gravity simulator that provides a constant offloading force to allow astronauts to experience lunar gravity on Earth terrain while being mobile at the same time. So our goals are in line with what Argos wants to accomplish. And we want the astronaut to be able to practice walking, kneeling, bending, and jumping while maintaining a constant offload. And for proof of concept, we want to offload at least 100 pounds from all the limbs and body. And the ultimate goal of this project is to demonstrate a proof of concept idea. So if NASA engineers think it's feasible, they'll pursue it with their own budget and own manpower.
So due to the complexity of our project, we've divided to split it into two different models. We have a dynamic small-scale model that will be used to represent the mobility of the frame. We will have a person with motion sensors, and we will show that we can control the motion of the wheels on the chassis with the movement of the person. So as the person moves, the frame will move. Then we have a static full-scale structure that will be used to demonstrate the offloading capabilities. So currently we have built a base for our static full-scale structure that will be mounted to the ground. We will be adding a linear rail to the top of the structure to provide for forward, backwards, and side-to-side motion. To provide the offloading, we will be using pulleys, counterweights, a cable, and a jerk wrist harness. We will have leg stirrups with this harness, and we will have different attachment points on the body so we can have the entire body feel the offload force.
The dynamic model is being designed such that the system will move autonomously with the subject. So it's made of aluminum 80-20 bars and has 8 pillow bearings mounted on top. Between the pillow bearings, there are 4 6-inch metal dowels that are suspended and support the aluminum arms. The shock absorbers shown below create the chassis suspension, and the wheels we chose are mechanism wheels. So these allow for translational movement in any direction without the need to reorient the system, which makes them the ideal choice for us. The motor shaft is significantly smaller than the 1.7-inch shaft needed to turn the mechanism wheels. Therefore, we fabricated an aluminum adapter that is capable of interfacing with the 2 varying shaft sizes. And we're using Xsens MTI series of GNSS sensors to control the autonomous movement of the chassis. 2 wirelessly transmitting sensors will be mounted on the front and back of the subject, relaying real-time data. This continuously updates the system of the subject's position and integrates the data from velocity to position. So on the bottom left, the picture shows the position of the subject.
This is our dynamic small-scale model of the chassis assembly. As you can see, the model is fully built and is similar to the CADIP model. There will be batteries at each corner to power each motor. The motor will turn the wheels based on the sensors. The sensors will be triggered by the motion of the person as they move around the area. The video shown here is a smaller model of a dynamic model. It was tested in various kinds of terrains around the campus and the movie efficient. In conclusion, the dynamic and static models shown here will be separate. The static model will demonstrate the offloading capabilities, while the dynamic model will prove that the ability of the sensors will send signals to the motors and wheels as the person moves around and walk around, and the chassis will follow them. Thank you.